Okay, we're going to get started. Good morning, everyone. Welcome to this session by Pat Viafore. He's going to be talking about extensible Python robustness through addition. Pat has requested that he will be taking questions after the presentation outside. So if you have any questions, please see him outside after the presentation. Take it away. Thank you.
Thank you. Hello, everyone. Welcome to PyCon. I like to start off by asking the audience a question. Who here works on a code base that is at least 1 year old? A show of hands. Okay, 5 years old? 10 years old? A lot of hands went down there. 20 years old? Not a lot of hands. I work on a code base that's 25 years old. I was in 5th grade when it was first started. Yeah, that makes my managers feel really old. Now, if you want to feel old, that's 1999. You're welcome. If you're successful in your job, do you want your code base to live for another 1 year, at least 1 year? Show of hands. Who wants their code to live for another 5 years? Still hands. 10 years? At least 20 years? Who wants to be working on their code in 20 years? Most hands went down, right? I like to say something about software development. It is both archaeology and time travel. It's archaeology. You're looking through the past, trying to determine the will of the ancients of why did they put this code in here? Why did they use a linked list? I don't know. You're trying to divine their intentions. But it's also time travel. We have to communicate to the future when we develop software. There's going to be people who are going to come after us, and they are going to be doing archaeology on their own. It's your job when you develop software that you need to deliver value in a timely manner. You don't want to take too long, and you want it to be useful. You have a secondary job, and this is what this talk is about. You want the people that come after you to be just as efficient as you are today. You don't want to leave a mess for them. My name is Pat Viafore. I'm going to be talking about extensibility in Python today. I'm going to be giving tips throughout here. This is my #1 tip. Think about the humans. Most of my talks are talks on empathy. They're just thinly disguised with technical content. We're going to have plenty of technical content, but think about the humans underneath. Software engineering is all about empathy. There are going to be people who have different jobs, different goals, aspirations, life goals, objectives, pitfalls, obstacles, things that get in their way. We're all human. Think about the people you work with, both now and in the future. So remember that throughout the entirety of this talk. So I'm going to start off with talking about some extensibility themes, some of the underpinning ideas that kind of lay the groundwork for extensibility. I want you to think about reducing your commit complexity. We're going to have a quick story time. I worked on a project. It was probably 10 years ago at this point. I needed to expose a on-off switch to a customer. A simple Boolean. This sounds easy. I had to update 3 files for my command line interface, 2 files for my network protocol, 2 files for my database, which was handwritten and all hard-coded. You want persistence, you actually want that to stay between reboots, that's another file. You want redundancy, another 2 files that have to be updated. About 12 files just to update a Boolean, just a true-false that a customer wants to say, yes, I want to click this switch that goes up. That sounds ridiculous, doesn't it? I want that to be in one place. I want to change things in one place. When I see lots of changes in a commit, I start thinking about something called shotgun surgery or spray and pray. People that say, yeah, I need to make a change, all over the code base. Good luck on that PR. You know what they say. You give a developer a 50-line PR, they'll find 50 issues. Give them a 500-line PR, yep, looks good to me. So I want you to consider how you reduce your commits. If every change in your system needs to be touching a multitude of files, I want you to look at reducing that. I want you to be mindful of OCP. What is OCP? OCP is the open-close principle coined by Bertrand Meyer. Code should be open to extension and closed for modification. Why do we care about this? Every time I modify existing code, I get worries. I get the jitters. I have regression tests to run. I have to talk through QA. I have to talk through my test plans. It's a nightmare. Like, you get scared. Yeah, I have all my tests, but what about the things that we didn't actually cover? You know, we may have 100% coverage, but that doesn't mean you're covering 100% of your functionality. So I want to limit the amount of change I make in code. I want to instead extend code, make my changes in new places that still changes functionality of my system. You might be asking, where do I split my code when I'm thinking about these things? So here's my advice for you. Are easy things hard to do? If you are constantly finding that adding a Boolean to your for your customer takes 12 files, that's hard to do. What if I forget one? What if my new hire a year from now forgets one? I want to make that easy. I just want to change it in one place. If you encounter pushback against similar features, this is a good idea that your system's not extensible. Hey, you built that admin page for us last week. Can you build us another page? It should only take a day like the last one. Oh, geez, I don't know. It's completely different. Be mindful of those. If you have consistently high estimates, those of you who use story points or time estimates, some people's like, yeah, anything that takes 2 weeks as a task, I need to break up into more granular subtasks. Maybe you should be making that task easier to be done. Do your commits contain large change sets? Something that's very easily checkable by automation. You can write a quick bash script to say, what's my average commit size? And are you mixing your policy changes with mechanism changes? What do I mean by policies and mechanisms? When I say policies, I'm talking about your business logic. These are the things that your business cares about. How are we doing inventory management? What deals are we offering to a customer? What is my SLAs for this pipeline availability? My mechanisms are the how I'm going to go do that. How am I doing data storage? How am I doing redundancy? How am I doing persistence? How am I doing caching? You want to separate your policies and your mechanisms. Reason being, your mechanisms can be reused. I can't tell you how many libraries I've gone into and say, this does exactly what I want it to do. Maybe I'm pulling in something for caching, but embedded right in the library are all of its policies. Oh yeah, caching is going to be an LRU cache. It's going to have an eviction time of a minute. And I'm going, my business case doesn't support that. I have a different business case. I want to tell you what my eviction time is. I want to tell you what my caching strategy is. If it's a pure mechanism, I can do that. I want to inject my policies into a mechanism. We see this in Python. Who here has ever written some code that when it fails to make a connection to your database or a network resource, it retries after so much time? Who here has written that? Who has written it in more than one function in their code base because it happens more than once? There's a fair amount of hands. Here's an example of a library called backoff. It's a decorator for a function. A decorator is a great way to deliver a mechanism. This package just lets me say, hey, I want exponential backoff. I want it to happen on an exception. I want you to wait for 60 seconds. And that's a really great way of doing this. I don't have to write this for every function. But the reason this works is because the policy, how I'm backing off, or the type of back off I'm doing, and the mechanism, which is the actual act of backing off and retrying, are separated. I can reuse back off anywhere I want in any code base because it's not embedding that policy decision in there. You'll see it in Flask well for my web devs out there. Login required. I don't want to see code on every single page that requires login, have 50 lines of code checking session management details. There's a nice mechanism for that. Let's reuse that mechanism because then I can extend my code faster. As you separate your policies and mechanisms, you start getting into data-driven designs. What do I mean by data-driven designs? It means that most of your policies are represented as data and not code. Let's look at some examples of what we see every day in Python ecosystems. So can you put your data in a collection? I mentioned that we have that one Boolean example. If I just had a list of all the Booleans and all the metadata associated with Boolean, does support redundancy, does support persistence, et cetera, I'm adding one line to a list to extend my functionality in my system. I'm not saying, oh, yep, I got to go code things up. You may have configuration files. Think of pyproject.toml. Like, that is a beautiful example of we put all of our policy decisions in a declarative file, a TOML file. Some other projects may use YAML files for other configuration files. The point being, my mechanisms consume my data, and I don't have to write code to do it. Your PM's eyes will light up when they ask for a change, and you say, I don't even need to redeploy. I got that. Persistence layers, also huge. If you have your databases, bucket storage, these are places that you can store data. The more you can put in declarative data formats, the better you're going to be off. I also want you to consider developing libraries first. What do I mean by this? Put your mechanisms in a library and treat it like an open source library, even if it's completely within organizational control. A good library should be README driven. Come from your customers first, your consumers first. If you are not familiar with README driven development, I highly recommend looking at it. Good libraries should have tests, because not only do they give you confidence that something actually works, but it also gives you documentation of how to use your code. A good library is easily consumable. This just doesn't mean, yep, I can pip install it. It means that there is documentation of how to use it. I don't have to set up long dependency chains of 30 other libraries just to get the toy example working. I want to be easily consuming your library, because if you put a high bar into how people consume your code, they're not going to use it. I like to see my libraries have clearly stated opinions. I mentioned separations of policies and mechanisms before. I'm going to pick on Black for a second. Black has mixed its policies and its mechanisms. Black's a popular formatter in Python ecosystem, and it is very opinionated about how it's going to do formatting. The actual formatting mechanisms and the rules are my policies. Black says, here are your policies, and you shall use them. But you know what? I'm okay with it, because they clearly state, here are the opinions. If that doesn't work for me, I look at it for another formatter, maybe one where I can inject my own policies into. I expect to see libraries releasable, release notes, they have versioning, they support branching if your actual product supports branching. You have a strategy of how you release these libraries. I expect your libraries themselves to be extensible, meaning that I expect people to be able to add on to your libraries quite easily. And I expect them to be composable. What do I mean by composable? Well, composability is another key piece for keeping extensible code. What that will give you is, you take your code and you can build other pieces of code up along with it. And let's take a look at Flask. These decorators are composable. I can use one of them, I can use both of them, I can use neither of them. If I need application routing, I have app.route. If I need login required, I have the aptly named login required. Composability allows us to take separate ideas and build them into our program. Think of it like kids playing with Lego blocks. I might give one kid 3 green blocks, 2 blues, and an orange, and they'll build something. I give it to a different kid, they're going to take those same building blocks and construct it into something different for their use case. My goal as a code developer is to support as many use cases as I can. I think about the people who have taken my code and used it for things that I never would have dreamed of. That's a great mark for good composable code. So create your building blocks. Keep them composable. And now I'm going to talk onto the meat of the actual Python pieces of this, of how we can see this in action. Architectural extensibility. I'm going to take a quick detour because I need to talk about an elephant in the room whenever we talk about how to extend code, and that's dependencies. Dependencies are crucial. You can't make code without a whole bunch of dependencies, but they also cause issues. You have to use them judiciously. I'm going to start by talking about physical dependencies. These are examples of physical dependencies. I'm importing from a module, the typing module I'm importing call. My module has a dependency on typing. I have some metadata class and it depends on the user. That's a physical dependency. I can see it in the code. Function calls are dependencies. We don't often think of them as such, but if my module calls a function from your module, I have a dependency on that function. And of course, at a higher level, we have packages. We depend on packages. When I look at physical dependencies, I kind of think of them like such. They're hard-coded into my source code. I can very easily see them like a function call. It's really easy to follow from A to B. If I have a big call stack, I can just control-click through my IDE, and I'll be able to figure out, yep, this is all the functions that are being called. They're very easy to understand. I can look at my code and see where all my dependencies are, my physical dependencies. They're really easy to find. Again, I can just control F or grep or whatever you want to do to search through a code base to find where is everything that calls this. But they're actually hard to change because they have this hard-coded nature in my system. And because of that, they're hard to substitute or mock out. So this makes it really tough to try to develop things that are quite flexible. They are understandable by static analysis tools, which is really nice because that means you can visualize your dependencies. When I talk about visualizing dependencies, I want you to think about 2 things. Something that has high fan out or something that has high fan in. A high fan out dependency, some things depend on it, but it depends on lots of things. These are typically your top level policies in your code base. This is saying, yep, Maybe I'm just dependent on my main, but I will depend on the rest of the system to get this working. These change quite often. High fan-in modules, these are the things at the bottom of your dependency tree. These are your mechanisms. These are going to be things like your decorators or your base classes, your functions that are using duck typing to the max. Lots of things depend on them. They don't depend on a lot of other things. When these change, you're going to have a bad time because so many things consume them. You can visualize your dependencies, like I said. So here's pip dep tree. This lets you show what the dependencies of your pip packages are, or your installed packages. I just have MyPy installed in a virtual environment, and I get a nice graph with the requirements and constraints of what actually I'm using. If you want to go a step deeper, these next two are going to look ugly, so just treat these as a snippet to what you can look into. PyDeps lets you take a look at all the modules that are depending. So this is from MyPy. I ran PyDeps on MyPy and saw where all the different modules of MyPy depended on one another. Again, I can use this to look at high fan in and high fan out to determine where my changes are happening and if they're happening in the right place. And if you want to even go down to the function call level, you can use pyan3, which will help you find out what your call graph is, determined at a static time. It's not checking runtime, but I can see which functions call each other. Again, physical dependencies are really, really easy to use with or to check through static analysis. We can use tools to visualize them. I mentioned high fan-in modules. They typically live at the bottom. What if those need to change a lot? What if you're making constant changes and breaking the rest of your organization every time you do? Because lots of things depend on them. Let's say you have A depends on B depends on C. Maybe A is something that wants something done, B is a message, and C is what's going to fulfill that for you. C needs to change quite often, and I don't want to impact A because of it. So what we're going to do, we're going to scratch that and reverse it. I'm going to make C depend on B. I'm injecting a dependency to do this, and we'll see some examples in a second of how to do this. The nice thing here, A doesn't have any knowledge what C is. There is no physical dependency from A to C. I can replace it with D or whatever. It doesn't really matter because A doesn't have that knowledge. I'm now starting to be able to extend my system, change functionality without changing existing code. And by existing code, I'm talking about A and B in this case. This introduces what I call a logical dependency. We deal with logical dependencies all the time. They're the things that happen at runtime. A depended on C to get that work done, even though it had no direct knowledge of it. I might make an HTTP request. Maybe I want to say that some pizza has been made. I don't know what endpoint is serving that. It could be on my computer. It could be in the lab down the hall. It could be in a different geographic location in the cloud. I don't have a physical dependency on that. When we deal with base classes, or really any super type relationship in Python, we're also dealing with logical dependencies. Maybe I'm using a factory to create some sort of pizza. There's going to be lots of pizza themed here. Thankfully, this is before lunch and not like at 5 p.m. when we're all hungry, because I'm going to talk about food a lot. If I deal with a base class, well, that's really nice. I'm depending on this interface, this abstract entity. I don't know how it's going to be served. And the cool thing is, it may not even be my organization that provides the derived class or the HTTP endpoint. So when we think about logical dependencies, they're typically determined at runtime. Readability will suffer because you can't just control click through. If you go click to your base class, you're not going to go find all the derived classes immediately, just through a simple search. Those might not even be in the same repository. And when readability suffers, debuggability suffers. Great, I'm making an HTTP request. I have a debugger up. How am I going to debug the computer that's serving that request? Do I have access to that? Is it in production? You're going to see debuggability suffer when you have a logical dependency. They're hard to find because, again, there is no physical link in that source code that's directly giving you evidence, but they're really easy to change. That means they're easy to substitute or mock out. We saw that with that C, I could make it D or whatever. I can change things. And yes, I am aware about monkey patching. I consider extensive monkey patching a code smell. Don't at me. With logical dependencies, we're not going to be understandable as static analysis tools. So there's not going to be nice code tools that can find these as easily. But why do we use them? They are crucial for abstraction. So I want you to think about trading off your dependencies judiciously. Now, I promised some Python examples. Let's look at event-driven architectures. What is an event-driven architecture? Well, an architecture is kind of the guiding principles about your code base and how it's structured, and events are stimuli. We have something that produces an event and something that consumes an event. For example, a kitchen timer goes off. The kitchen timer is the producer, the event goes off, and there's a consumer, a chef who's rushing to get a casserole from the oven. Maybe an alarm clock's going off. The alarm clock is your producer, the act of it going off is an event, and the consumer is some late sleeper who then acts upon it. They wake up. Let's imagine I have some order management system. I'm completing my order. I package it and I notify the customer that it's done and I notify a restaurant that it's done. And I want to extend this. Maybe sales wants to know. Maybe my vendor wants to know for inventory. Maybe I'm doing drone delivery and I need to let the drone supplier know. I don't want to have to keep modifying this code when all new cases come up. So again, we're talking about architectural extensibility. What can we do? Well, I have this producer. It depends on a transport, which in this case are just function calls. And those are the consumers. Well, scratch that. Let's reverse it. I want the consumer to depend on the transport. And this is what gives us an event-driven architecture. We have producers that depend on a message broker. We have subscribers that depend on a message broker. A message broker is just, think of it like the post office. It gets a topic, a name, so yep, I'm going to route this to the right people. Producers don't know about subscribers. Subscribers do not know about producers. I can add either, and the system's unchanged. If I want to have, maybe I'm franchising my restaurant and I have multiple places that are producing meal done notifications, I can add producers, no subscribers have to change. Hey, I want my vendor to start getting notified when an order is done. I add a subscriber, none of the producers have to change. Let's see this in action. I'm going to be talking about PyPubSub. It is just one example of how to do this. It is an in-process message broker. You can use other systems, there's Kafka, you can use Redis as this, you can use RabbitMQ, whatever you want to use. The advice I'm giving will apply to all of them generally, but let's see how we do this in PyPubSub. This is my subscriber. I have, from PubSub, I'm importing pub, I have some function that actually does the work. The customer wants to know when a meal is done. And I'm going to subscribe to a topic. That's that string meal done on the far right of the screen. And I'm saying when I receive this topic, when I receive this event, I want you to call notify customer that meal is done. This is in its own file. In a different file, I'm importing PubSub as well. And when I complete the order, this is my publisher. I package the order, and then I just publish to meal done. There's no enumeration of all my subscribers here. There is no knowledge of this publisher to any of the subscribers. This is extensibility in action. This is open-close principle in action. I can add new subscribers and new files and never touch the code that's publishing. All we depend upon is the message, the concrete information we pass back and forth. The publisher and subscriber may have a dependency on what that message type is, but as long as that's not changing, I can keep adding at will. So my advice for this is use event-driven architectures to decouple your producers and your consumers. Now, event-driven architectures aren't the only way that we can see extensibility in Python. I also like pluggable architectures. And I'm going to kind of zoom in and look at something on the small line, but to give a kind of an analogy to pluggable architectures, think about your stand mixer. Maybe it's in your kitchen, in a parent's kitchen, in a friend's kitchen. I want to whisk some eggs. I turn the stand mixer on, and the little whisk goes round and round. I get whisked eggs. What happens when I want to make dough? Do I buy a new stand mixer for that? No. I buy a dough hook that attaches into my stand mixer, and it turns the dough around. Do I need a general mixing? I'll get a flat blade. This is pluggable architecture at work. I am plugging in attachments without having to rebuy a whole new system. And it works because there is a defined interface point between the system and the plugin. In this case, it's where the attachment connects to the stand mixer. We use plugins all the time in the Python ecosystem. PyTest. So many plugins exist for PyTest for different output formats, different ways of testing things. Poetry. You can add plugins that parse custom PyProject TOML files that just work with poetry. It's really nice. I don't have to change poetry source code every time I want a new thing in my TOML file. Hypothesis, I can plug in new strategies for generative testing. I don't have to rewrite hypothesis to get that. Pilot, you can write your own linters through their plugin system. These are all examples of a defined interface that allow you to plug in your own code that's pretty much divorced from the original source code, and it just works in that ecosystem. Let's look at two examples of how to do this. I'm first talking how to plug into algorithms. If you're familiar with a template method pattern, this is very similar to that. Let's imagine I have some algorithm and there's some steps that I want to be developer overrideable. A lot of people reach for subclasses first. A lot of people just will hard code that right into the algorithm itself of, oh, if this is, option A, go do this different thing. That's modifying our code. I want to extend our code. I mentioned I'm going to talk about pizzas. Let's say I have an algorithm for making pizzas. I prepare some ingredients, I roll out a pizza base, I add my pre-baked toppings, I bake it, add post-baked toppings, delicious. I want the developer to be able to override those because maybe they want to make pizzas I've never even dreamed of. I'm going to start by making a data class. These are just callable functions. Prepare ingredients, add pre-baked toppings, add post-baked toppings. These are the things I want to be overrideable. In my create pizza function, I just take that as an argument. This is injecting that dependency. Think back to when I reversed the physical dependency to a logical dependency, and I said, here, how do you inject a dependency? Here's how. You pass it in to your function parameter or your function argument list. So I'm delegating to my pizza creation functions to actually do the things that may change at runtime. Now I can do all sorts of cool things. Maybe originally my system did Italian or Chicago or deep dish pizzas or Detroit style pizzas, whatever. Maybe I want a Lebanese pizza with za'atar meat halloumi. Sounds delicious. Yeah. Someone knows what's up. We just pass in new functions. Like, this looks like stupidly simple, and that's because it is. I can add new pizzas, and it's really not that hard. Wait 2 hours. It'll be lunchtime. The audience member said, now I'm hungry. If I want a Korean pizza, I just change the functions. Look at the difference between a Lebanese pizza and a Korean pizza. The create pizza function is the same. I'm just injecting new dependencies into here. Cook some bulgogi, add it, and give me some scallions and sesame oil. Also delicious. Now, that's kind of a smaller how do I plug into algorithms. I also want to talk about how you can plug into packages. This is a really cool way of doing plugins. I'm going to talk about Stevedore. It's just my favorite package to do this. Pluggy is also very popular in the Python ecosystem. What it's going to let me do is it's going to let me plug into packages. So let's imagine I have this kitchen robot that I want to build, and it's completely powered by Python because, hey, Python's awesome. And I want other people, other organizations to create plugin modules, just like a stand mixer. Maybe someone for Tex-Mex, someone for Linguini. Off the shelf, customers can just buy what they want. I have this protocol, Ultimate Kitchen Assistant module, and for slideware, yes, it's simple. Bear with me. It has a list of ingredients, it gets some recipes, and then there's an actual function to prepare the dish. Here's an example of one. Here's my pasta module. It gives you a whole bunch of ingredients, and you can pretend that the implementation does whatever complex thing you want it to do here. With Stevedore, I can look for all installed plugins and do operations on them. So I'm using an extension manager here. This is great for querying every plugin in your system. It works by using a namespace, in this case, my Ultimate Kitchen Assistant Recipe Maker. You'll see that that is just a manager, and I am just iterating through every plugin's list of recipes, and I'm chaining them together. So I can use Stevedore to say, yep, you provide a plugin, I can query it. Stevedore becomes that attachment point, just like in a stand mixer. And the cool thing is, it can be in different packages. As long as your entry points, and this works in poetry as well, just doesn't look like setup tool style. But as long as I have entry points that use that same namespace, I can get new functionality just by pip installing a new package. Let that sink in. I can change the functionality of my code without modifying any of that code just by downloading a new package. That's pretty cool. So use pluggable Python for extension points. I've talked about 10 topics today. I hope you think of all these. Number 0 is I think the most important. Think about the humans, because if we're not thinking about them, we're not going to do any of these other things. I'm going to leave you with one last one. Don't overextend yourself. It's very easy to say, yep, I learned about extensibility, I'm going to use it everywhere. No. Use it where it makes sense, where things change often. Otherwise, you'll have a mess. Anyone who remembers design pattern fever of the 90s will know what I'm talking about. I'm Pat Viafore. I'm a principal software engineer at Cloud Software Group. I own a consulting company called Coursera. I'm the author of Robust Python, which this talk is pulled from, part 3 from that book. And if you're ever in North Alabama, come check out Huntsville Pi. Thank you so much. Enjoy the rest of PyCon. And if there's any questions, I'll see you out in the hall.